When we're considering a field extension, one of the most important metrics that we can use for understanding its structure is the dimension of the larger field as a vector space over the smaller one. This number is going to be what we call the degree of the extension and is going to be a very important metric for us to understand and take advantage of when looking at the structure of field extensions in general. So starting with the definition 170 says let f contained in E be a field extension. The dimension of E as an F vector space is called the degree of E over F and is denoted this way as E colon F in square brackets. This is the same notation that we used when looking at the order of a subgroup inside a larger group. In this case, we're calling this the degree. Now, if E is a finite dimensional vector space, that is, if the degree of the field extension f to E is finite, then we say that E is a finite extension of F, and otherwise E is said to be an infinite extension of F. Now, this finishes the definition, and the ideas of a finite extension and an algebraic extension are going to be related to one another, although it turns out that the two notions are not completely the same, but we'll see that in a moment. Let's look at a few examples. So if A in some extension E is algebraic over F with minimal polynomial P, then we have that the field F of A is isomorphic to the field F adjoin X mod the ideal generated by P by Theorem 170. Oh, I called this definition 170. This is actually definition 171. So in particular, we can describe a basis for this vector space on the right as an F vector space. So 1 bar x squared bar up to xn minus 1 bar is a basis for the field on the right, fx mod p, where n is the dimension of p. Thus, in this case, we have that the degree of the extension f of a over f is equal to, because that is the dimension of the field f of a as a vector space over f. So we're going to use this fairly often, where if we have an algebraic element and we know that its minimal polynomial has degree n, then the field extension that we get by adding in a root of that root has degree equal to the degree of that minimal polynomial. And in particular, if we have that an element A is the root of some polynomial of degree n, then the degree of that extension is less than or equal to the degree of that polynomial. For the further example, if A is transcendental over F, then the degree of the extension f of A over F is infinity, since f of A is isomorphic to the field f of x, the fraction field of the polynomial ring f join x, and f join x has no finite basis. For a final one that's going to be useful to us for intuitively understanding some of the later theorems, by Theorem 155, if E is a finite extension of F, then E is isomorphic to F E colon F, F to the degree of E over F as F vector spaces. And this is because Theorem 155 shows us that any finite dimensional vector space is isomorphic as an F vector space to the vector space Fn, where n is the dimension of that vector space. Now, as I mentioned, the ideas of being a finite extension and being an algebraic extension are related, even though they're not quite the same. Theorem 172 gives us that relationship. If E is a finite extension of F, then E is algebraic. So a finite extension is algebraic. The reverse is not necessarily the case, as we'll see later. Furthermore, we can go even further here, and the minimal polynomial of any element A in E has degree at most the degree of E over F. So a finite extension has a couple of very important properties. A finite extension is algebraic, meaning that every element of E is the root of some polynomial over F. Furthermore, the minimal polynomial of these things have degrees that are bounded by the degree of the extension. So let's look at the proof of this. Proof of this is not terribly difficult as long as you've got the right idea in mind. So let's let n be the degree of E over F, and let's let A belong to E. Now we can look at the set 1a squared, a cubed, up to an. Now you'll notice that this set has n plus 1 elements in it. Any set of order greater than the dimension of a vector space has to be linearly dependent over the base field. So this has size n plus 1, and so this set is linearly dependent over F. So that means that there exist BI elements of the field F such that there's a linear combination of these things, which is 0. such that 0 is equal to b0 times 1 plus b1a plus b2a squared, etc., plus bn a to the n. So that means that a is a root of the polynomial b0 plus b1x plus b2x squared plus etc., plus bn x to the n. That means that A is algebraic. And furthermore, because A is the root of some polynomial of degree n, the minimal polynomial of A must have degree less than or equal to n. I should say A is algebraic over F. Now, as I mentioned, the converse to Theorem 172 doesn't hold. It's possible to have an algebraic extension which is not finite. For a very specific example, the extension Q contained in the field containing Q and the square root of 2 and the cube root of 2 and the fourth root of 2 and the fifth root of 2, etc., is algebraic. Now, this takes a little bit of work. One of the exercises is going to be that if you take the minimal field containing a set of algebraic elements, that field itself is algebraic by showing that the sum, difference, product, and inverse of any algebraic elements is itself algebraic. So this extension is algebraic since the nth root of 2 is a root of the polynomial x to the n minus 2, but it is not finite since x to the n minus 2 is in fact a minimal polynomial of the square root of n over 2 for each n. We can show this simply by showing that this is irreducible. Eisenstein's criterion is the easiest way to do that. So these x to the n minus 2 polynomials are all irreducible polynomials. They are monic, and the nth root of 2 is a root of this x to the n minus 2 polynomial. Therefore, all the elements in the larger field here have minimal polynomials with unbounded degrees. If this extension were finite, then every element of it would have a minimal polynomial that had a degree less than or equal to the degree of the extension. And so because the minimal polynomials are unbounded in their degree, that means that we can't be looking at a finite extension here. Now, the next step in our study of the structure of field extensions is to see what happens when we have a sequence of extensions, or equivalently, a field extension and a field that sits between the two, larger than the base field but smaller than the whole thing. Theorem 173 is key to understanding how this works. And it's really going to be talking about finite extensions here. And a lot of what we're going to do next, going forward, it has to do with finite extensions, which are themselves algebraic. But we are going to be able to come back and talk about algebraic extensions in general near the end of this section. So, Theorem 173 says that if f contained in E and E contained in K are finite extensions, then f contained in K is a finite extension. the composition, if you like, of two finite extensions is itself finite. And furthermore, we have that the degree of k over f is equal to the degree of k over e times the degree of e over f. This relationship here is going to be very important to us because it allows us to take information about the two extensions and give us information about the composition of them. And we'll see that in complex situations where we have, say, lots of different fields sitting between f and k, we can use this property to understand the relationships between them better. The second part of this theorem says that if we have a chain of extensions, field extensions, and the containment and the extension f to k is finite, then the extensions f to e and e to k are finite. And once we have that the extensions f to e and e to k are finite, then the first part of the theorem kicks in, and we have this same equation. We have again that the degree of k over f is equal to the degree of k over e and the degree of e over f. Now, the most rigorous way of proving this you'll find in the notes, and the best way of proving this is to assume that you have a basis for e over f, which is not necessarily finite, and a basis for k over e, which is not necessarily finite, and use that to prove that you can construct a basis for k over f, for k as an f vector space, where the size, the cardinality of that basis is equal to the cardinality of the Cartesian product of the bases of e over f and k over e. So I'm not going to go through that whole thing here. We're going to give here a more intuitive idea of the proof, which is more helpful for understanding what's going on, as I say, intuitively. But the formal proof looks like the following. Looks like, let's let bi, where I belongs to fancy I, be a basis for e over f. So basis for e as an f vector space. Let cj, for little j in fancy j, be a basis for k over e. So that means that every element of k can be expressed uniquely as an e linear combination of the cj's, and every element of e can be expressed uniquely as an f linear combination of the bi's. So this shows that if we look at the elements bi, cj, these are all elements of k because everything inside is contained in k, and where we take all the possible combinations here for I and j in the Cartesian product of fancy I and fancy j, that this is a basis for k over f. And this is not terribly difficult. It's just you prove that they're linearly independent by using the fact that the CJs are linearly independent, and then that the BIs are linearly independent, and you show that this set spans K as an F vector space by using the fact that it spans K as an E vector space, and then every element of E lies in the span of the BIs as an F vector space. and so forth and so on. So that means that the degree of k over f is equal to the dimension of k as an f vector space, which will be the Cartesian product, the cardinality of the Cartesian product of I and j. And so from here we show that if I and j are both finite sets, then the magnitude, the cardinality rather, of the Cartesian product is just the product of their cardinalities. I forgot to say, if these are both finite, then this is the case. And then if I is infinity, or if I has infinite cardinality or j has infinite cardinality, then the Cartesian product will have infinite cardinality as well. And that's the basic idea behind it. The only work comes in this step here, where you show that these BICJs are a basis for K. So this is the basic idea of the formal proof. The intuitive proof that I wanted to mention looks like the following. By definition, we have that K is equal to E, or is isomorphic as E vector spaces to K to E to the degree of K over E. Now, since F is a subset of E, every E vector space is also an F vector space. And in particular, any isomorphism of E vector spaces will also be an isomorphism of F vector spaces. So they are isomorphic as E vector spaces, hence they are isomorphic as F vector spaces. And we also have that E is isomorphic to F to the degree of E over F as F vector spaces. So that means that K is isomorphic to E, the degree of K over E, which is isomorphic to F to the degree of E over F to the degree of K over E, which is F to the degree of K over E times the degree of E over F. So this shows that K is isomorphic to the vector space F to this product, which shows what we want. It shows that as a K vector space, K has dimension equal to, as an F vector space, K has a dimension equal to the degree of K over E times the degree of E over F. Now, this is only an intuitive proof, not rigorous, because we're using facts about how this notation that we're using rules of exponents on vector spaces that need some justification. They are true, and it turns out that at least as long as all the numbers involved are finite, all these isomorphisms that we've written down are correct, but we do need some additional justification to make everything perfectly rigorous here. And also, this argument doesn't really handle the case of showing that things work out properly when all you know is that K is finite over F. It doesn't handle the second part of the theorem quite as well. So that's why I wanted to give both of them. This intuition, though, is very, very good for us to keep in mind. Remember that every vector space of finite dimension is isomorphic to just a vector space of the form Fn for some n. All right, now what's going to go on here is that we can use this idea of measuring the degree of an extension by looking at the degrees of little sub-extensions to construct webs of subfields of a given extension. So we often use notation, or not even notation, diagrams, like the following, to describe webs of sub-extension fields. So in our example, we had K, we had F, and we had E. And what we will do is we will often draw these lines here, and they indicate that the fields higher on the page are extensions of the lower ones. Furthermore, we will often label these bars with the degree of the extension. So this bar going from F to E, we will label with the degree, and that shows basically how much bigger E is than F as an F vector space. And then we'll have the bar from E to K be labeled with the degree of E over K, or K over E, rather. And then this one we can label as the degree of K over F, but we also know from the previous theorem that this is equal to K over E times E, the degree of E over F. So the idea is that the degree of an extension in one of these diagrams is equal to the product of the degrees of the extensions along any path. The degree of let me make this somewhat more precise. The degree of an extension from, I'll just say from A to B in a diagram, where A and B are just some field in the diagram, is equal to the product of the degrees of extensions along any path from A to B. So in this case, we could get from F to K just by going directly up F to K, and we label that extension with the degree of K over F. What Theorem 173 says is that that number will be the same as the number that we get when we go from F to K along any other path and multiply all the degrees of the extensions as we move along. So let's look at a couple of examples. So let's consider the field extensions Q contained in Q adjoining the square root of 2, contained in Q adjoining the square root of 2, comma I. We looked at this in a previous section. Now we have that Q of square root of 2, the degree of Q square root of 2 over Q is equal to 2. Since x squared minus 2 is a minimal polynomial of the square root of 2. Now, we also have that the degree of Q square root of 2 comma I over Q square root of 2 is equal to 2. Since x squared plus 1 is the minimal polynomial of I in the polynomial ring q square root of 2 adjoin x. So here we need to be a little bit careful, because now if we want to study this field extension from q square root of 2i over q square root of 2, we need to ask what is the degree of the minimal polynomial of I over q square root of 2. And in this case, we can see that x squared minus 1 is still a polynomial that has I as a root when considered over the field q square root of 2. And so we just need to show, is this a minimal polynomial? And because it's degree 2, the easiest way to do that is just to show that it has no roots in q square root of 2. And in fact, we know that in the whole complex numbers, the only roots of x squared minus 1 are I and negative I, and the field q square root of 2 is not going to include any of those. So we know that x squared minus 1 is going to be irreducible over this polynomial, or irreducible in this polynomial ring. Therefore, it's a minimal polynomial of I, and so its degree gives us the degree of this extension. So we can use this to conclude that the degree of q square root of 2i over q is equal to 4. So as a q vector space, the polynomial, the field q of square root of 2 and I has dimension 4 over q. In fact, we can see exactly what that looks like by seeing that all elements of this field can be written in the form a plus b square root of 2 plus ci plus d square root of 2i, where a, b, c, and d belong to q. When we just look at these expressions here, it's not totally obvious that every element of this field can be expressed uniquely using an expression of the form a, b, c, d with square root of 2i and square root of 2i, square root of 2 times I. But this argument shows that it is. Theorem 173 shows that the degree of this extension is 4. Therefore, this field q square root of 2i has degree 4 over q, or has dimension 4 as a q vector space. So we can sketch out the diagram of what this looks like. Q of square root of 2i, then q down here, and we just found that it has degree 4 by looking at the fact that we've got q square root of 2, which is degree 2 over q, and q square root of 2i has degree 2 over q square root of 2. Now there's another subfield that we might consider here, and that's q of I, so the smallest field that contains both the rationals and the imaginary number I. Well, x squared plus 1 is still a minimal polynomial for I over q, and so this extension has degree 2. So this is because x squared plus 1 is a minimal polynomial for I over q. And so now when we look at this extension here, from q of I to q square root of 2i, we must have that when we look at the chain of extensions going from q to q of I up to the top field, and we multiply all those degrees together, we get the same result as when we go along any other path. So as we go along here, we should get the same result as when we go directly, or as we go through the other subfield of q square root of 2. So because of all of this, we have that this is 2. Because 2 times 2 gives us 4. To be more explicit about what's going on here, we could say that we have that 4 is equal to the degree of q square root of 2i over q. And then by theorem 173, this is equal to the degree of q square root of 2I over q of I times the degree of qi over q. And so, because this part is equal to 2, we can conclude that the degree of q square root of 2I over qi is equal to 2. So we can get this web of subfields, of subfield extensions of the larger field extension. All right, let's look at a slightly more complicated example. We're not going to go through all of the details here, but you can find them all in the notes. So let's consider the field extension Q contained in, I'm going to call it E, and that's going to be Q of alpha 1, alpha 2, alpha 3, where alpha 1 is the square root of 2, alpha 2 is the cube root of 3, and alpha 3 is the fourth root of 5. So we're going to look at the smallest field that we can get that contains the rational numbers and these three irrational numbers. So what we're going to do is we're going to draw again a big web of subfields. In this case, instead of just having the 4 fields that we had last time, we have 8. So we're going to have the field E at the top, the field Q at the bottom, and we're going to spend some time filling in the fields in the middle, some of the fields in the middle, and the degrees of their extension. So if we start with Q and we go up basically one step, we could get Q of alpha 1, Q of alpha 2, and Q of alpha 3. Now each of these extensions will have some degree. We'll get to that. And then above that, we'd have Q of alpha 1, alpha 2, Q of alpha 1, alpha 3, and then Q of alpha 2, alpha 3. And here we can fill in some more containments. Q alpha 1 is contained in Q alpha 1, alpha 2, and Q alpha 1, alpha 3. Q alpha 2 is contained in Q alpha 1, alpha 2, and Q alpha 2, alpha 3. And then Q alpha 3 is contained in Q alpha 2, alpha 3, and Q alpha 1, alpha 3. And these three ones are all contained in the top. And we want to know, we would like to fill in the degrees of all of these extensions. Now, the first thing that we can note is that we can find the minimal polynomials of alpha 1, alpha 2, and alpha 3 over Q, which are going to give us these bottom degrees. So for alpha 1, we have x squared minus 2, because alpha 1 is the square root of 2. And we know that this is the minimal polynomial because it's monic and it's irreducible. Again, Eisenstein's criterion is the easiest way to do it in this case. Alpha 2 has minimal polynomial x cubed minus 3, and alpha 3 has minimal polynomial x to the fourth minus 5. All of these are irreducible by Eisenstein's criterion. They're all monic by inspection, and so in particular we have that the degree of Q alpha 1 over Q is equal to 2, the degree of this minimal polynomial. The degree of Q alpha 2 over Q is equal to 3, and the degree of Q alpha 3 over Q is equal to 4. So we can fill in those three degrees right here. Now, this allows us to tell something about the degree of E over Q right away. So this tells us that E over Q has to be equal to the degree that you get when you multiply the degrees going along any path, starting at Q down here at the bottom and going up to E. So that means that the degree of E over Q is divisible by 2, 3, and 4. So this means that E over Q is a multiple of 12. So we have that E over Q is equal to 12n for some number n, some integer n. Okay, we can go further than this. So when we start moving to these, considering the degrees higher up on the page, it's conceivable that some of these polynomials will no longer be irreducible, because as we move up, we're looking at polynomials sitting over coefficient fields that are larger. And so we have to be careful to check and see whether they're irreducible anymore or not. But what we can say is that every time we add in, we go from one of these fields and add in an alpha 1, then the degree of that extension is at most 2. Every time we add in an alpha 2, the degree of that extension is at most 3, and the degree of every time we add an alpha 3, the degree of that extension is at most 4. And the reason for that is that even if these polynomials wind up not being irreducible, no matter what field we're looking at, these polynomials are always polynomials that have the alpha 1, alpha 2, and alpha 3 as roots. So for instance, when we go from Q alpha 1 to Q alpha 1 alpha 2, we've taken an extension where we're adding in alpha 2. Now, alpha 2 is the root of a degree 3 polynomial, whether or not, over Q alpha 1, over this field. Whether or not it's irreducible, we don't know, but we do know that the degree of this extension will be less than or equal to 3. If this is irreducible, it'll be equal to 3. If it's not irreducible, then the minimal polynomial of alpha 2 over this field, Q alpha 1, has degree less than 3. And similarly, moving from Q alpha 1 alpha 2 up to E means that we're including alpha 3 now, and the degree of that extension is less than or equal to 4. It might be less, but it might be 4, but it might be less. So what that tells us is that the degree of E over Q is less than or equal to 2 times 3 times 4. 2 times 3 times 4 is 24. So we've actually narrowed down the degree of E over Q to 2 possible numbers. It has to be a multiple of 12, and it has to be less than or equal to 24. So combining these two things together, we have that E over Q is equal to 12 or 24. So this is what we've got so far. In order to push push further, we need to do one more thing, which is complex. It takes quite a bit of computation, and again, I'm not going to go through all of the computation because it's messy, but all the details are in the notes. So let's look at the situation that we have and see how we can improve. Now let me erase these things that we don't need anymore. here's what we've got. What we would like to do is start filling in some of these other degrees more specifically. We have that this one is less than or equal to 3, this one is less than or equal to 4. And in this case, it's going to be most useful actually to start here and start considering the degrees of these fields, Q alpha 1, alpha 3, and Q alpha 2, alpha 3, over the field Q alpha 3. Now, part of that reason is because we're kind of already starting as large as we can. In this first step, we could choose to go up the path of degree 2, path of degree 3, or path of degree 4. The path of degree 4 just gets us the furthest. 4 is the highest, and so we could go there easiest. Now, from there, we've got to decide whether we should look at the extension from Q alpha 3 to alpha 1 alpha 3 or alpha 2 alpha 3. Now, the way that I think about this and the way I make this choice is that this extension, the extension of E over Q, has to be equal to either 12 or 24. Now, if we go along this path, we've already multiplied by 4. And we know that one of these branches from Q alpha 3 going up are going to have to involve a degree extension of size 3. Or size that's a multiple of 3, because when we multiply all of the degrees along the paths up, we need to get either 12 or 24, both of which are divisible by 3. And so we already know that. So I want to look at the other one. I want to look at what happens when we go along the path that can't have a degree of 3. When we go from Q alpha 3 to Q alpha 1 alpha 3, we're throwing in alpha 1. And we remember that alpha 1 is the root of a polynomial of degree 2, which means this, the path from Q alpha 3 to Q alpha 1 alpha 3 has to have degree less than or equal to 2, which means it has to have degree 1 or 2. Now, if it's 1, that would mean that these two fields are actually the same, that we've written them out separately, but they're actually the same, which can happen, in which case we'll rewrite our diagram. Now, if that happens, then when we follow the paths of the extension fields from Q to Q alpha 3 up to Q alpha 1 alpha 3, we will either have a combined degree of 4 or 8. Now, when we go from Q alpha 1 alpha 3 up to E, that's throwing in an alpha 2, because the alpha 2 piece is what we're missing, going from this field up to here. And we know that alpha 2 is the root of a polynomial of degree 3. So we know that this degree is less than or equal to 3. So in particular, that means it's 1, 2, or 3. Now, if this is going to be either 4 or 8, and this has to be equal to, and the whole thing has to be equal to either 12 or 24, then the only one of these possibilities that exists is that it has to be 3. 3 is the only degree that we could possibly put in here, so that multiplying along these paths gives us either 12 or 24. So, given all that, determining whether the degree of E over Q is 12 or 24 can be determined by saying, is the degree of Q alpha 1 alpha 3 over Q alpha 3 equal to 1 or 2? Now, remember that alpha 1 is equal to the square root of 2. Alpha 3 is equal to the fourth root of 5. And so we know that x squared minus 2 is inside the polynomial q alpha 3 of x has alpha 1 as a root. So the question is x squared minus 2 inside this field q alpha 3 adjoin x irreducible? If it is, then it's a minimal polynomial for alpha 1 over this field, in which case the degree of this extension is 2. And if not, then that means that that this isn't the minimal polynomial. So the minimal polynomial has lower degree, which means that the degree extension would be 1. Now, since x squared minus 2 is of degree 2, remember that we can detect whether a polynomial is irreducible. A polynomial of degree 2 or 3, we can determine whether it's irreducible by checking to see if it has any roots. So it is irreducible if it has no roots in q of alpha 3. So we just need to see, is this the case? Can we find a root of x squared minus 2 in the field q alpha 3? Now, this, I'm going to move to another page for this. So the question we consider right now is, does there exist an element, I'll call it an element y in q alpha 3, such that y squared minus 2 equals 0. Now, to check that out, we need to know what the elements of q alpha 3 look like. But we have that. We have that q alpha 3 has a basis made up of 1 alpha 3, alpha 3 squared, and alpha 3 cubed, because because the degree of q alpha 3 over q is equal to 4. And this is how we get a basis of q alpha 3 over q as a vector space. So we can say that the elements of q alpha 3 look like a plus b alpha 3 plus c alpha 3 squared plus d alpha 3 cubed, where a, b, c, and d come from q. So now we can ask, do there exist a, b, c, and d in q such that a plus b alpha 3 plus c alpha 3 squared plus d alpha 3 cubed squared minus 2 equals 0. And here's where the computation comes in, because what we're going to do now is we're going to expand this and then start combining things together, and using the fact that every time we have alpha 3 to the 4th, we can replace that with 5. And so the first step here, let me write it actually going the other direction. If we expand all this out, we get a squared plus 2ab alpha 3 plus And then we'll get 2ac plus b squared alpha 3 squared plus 2ad plus 2bc alpha 3 cubed plus, and then 2bd plus c squared alpha 3 to the fourth plus 2cd alpha 3 to the fifth plus d squared alpha 3 to the sixth minus 2. And then we reduce everything using the fact that anytime we see a fourth power of a cubed, we can just replace that with 5. And we can write this as a squared, and then plus 10bd plus 5c squared minus 2. So there's the essentially the coefficient of a3 to the 0th, taking parts from here, here, and here. Plus, and now for the coefficient of a3, we'd have 2ab from this second term, and then from 2cd a3 to the fifth, a3 to the fifth is equal to 5 times a3, so we get plus 10cd times alpha 3, plus, now for alpha 3 squared, we're going to have 2ac plus b squared plus, now a3 to the sixth becomes 5d squared times a3 squared, and then plus 2bd plus c squared times I went to the wrong spot. And then we just have 2ad plus 2bc times alpha 3 cubed. So we have that 0 is equal to this expression here. But remember that these elements, 1, alpha 3 squared, and alpha 3 cubed, form a basis for the field q alpha 3 over q, which means that each of these coefficients down here in this last expression must be 0 in order for the whole thing to be 0. So in order for this to be the case, we must have that a squared plus 10bd plus 5c squared minus 2 equals 0, 2ab plus 10cd equals 0, 2ac plus b squared plus 5d squared equals 0, and 2ad plus 2bc equals 0. And the point is that you can show that if the a, b, c, and d are all restricted to being rational numbers, which they are, that this has no solution. So this has no solution with a, b, c, and d being rational numbers. And this uses at various times throughout the process the fact that square root of 2 is irrational, the fact that square root of 5 is irrational, which makes sense because we're using 5s and 2s as part of our alpha 1s and alpha 3s. So the point is this has no solution if a, b, c, and d all have to be rational. So this means that x squared minus 2 has no roots in q alpha 3. So that means that the expression x squared minus 2 in q alpha 3 adjoin x is irreducible. And so that means that x squared minus 2 is the minimal polynomial of alpha 1 over the field q alpha 3. So that means that the field Q alpha 1 alpha 3 over Q alpha 3 is equal to 2. So now we actually have determined the degree of this extension, the last extension that we needed to fill in that path in the diagram. So going back to the diagram, we'll copy it and then fill in the rest of it. So this is what we've got so far. Let me copy it and then I'll erase the pieces that we don't need. All right, so this is what we had before. And what we've done is we've just determined that the degree of Q alpha 1 alpha 3 over Q alpha 3 is actually equal to 2. So that means that we can in fact conclude that that the degree of E over Q is actually equal to 24. Now, there are a lot of things that we can conclude based on that. First of all, remember that when we got 24 as the maximum possible from before, that came from following this left-hand path up, where we noted that the degrees of these two extensions were at most 3 and at most 4. But in fact, if they are any less than that, we won't get 24 out of this. If we follow the path from Q up to E along any path and multiply all the degrees together, we have to get exactly 24. And so that means that these degrees along here have to be exactly 3 and exactly 4. And now we can start using the same sort of ideas to figure out the other degrees in the diagram. And from here, it actually goes pretty quickly. So now, let me see if I can use some colors here to make things clear. If I go from Q to Q alpha 1 to Q alpha 1 alpha 2, what we get is that this whole extension has degree 6. But if I go from Q to Q alpha 2 to Q alpha 1 alpha 2, that also has to have degree 6. Now I know that the degree from Q to Q alpha 2 is 3, which means that the other part of it has to have degree 2. Because no matter how I get from Q to Q alpha 1 alpha 2, if I multiply the degrees of the extensions together as I go along those paths, I should always get the same thing, in this case 6. So that gives the degrees that we've got there. Let me erase these things so things don't get super cluttered. All right, now let's handle this degree from Q alpha 1 to Q alpha 1 alpha 3. So in this case, we can look along the path from going from the two paths going from Q to Q alpha 1 alpha 3. If we go from Q to Q alpha 3 to Q alpha 1 alpha 3, we can see that the total degree of this extension is 8 because we've got 4 and then 2. Their product is 8. If we go the other way from Q to Q alpha 1 to Q alpha 1 alpha 3, that product should also be 8. We've already got 2 from Q to Q alpha 1, so going from alpha 1 to alpha 1 alpha 3 should have degree 4. And then let's see, what do we have left? Now we can use a similar argument on this right-hand side over here that we used on the left-hand side. To go from alpha 3 to alpha 2 alpha 3, that has degree less than or equal to 3, because alpha 2 is the root of a degree 3 polynomial. And going from Q alpha 2 alpha 3 up to E has degree less than or equal to 2, because we're adding an alpha 1, which is the root of a degree 2 polynomial. And once again, we can see that these less than or equals actually have to be equals, because otherwise we wouldn't get a large enough degree when following up the right-hand path. So we have that this path has degree 3, this one has degree 2, and now the only one left is the path going from Q alpha 2 to Q alpha 2 alpha 3. We want to know that extension. And if we consider the extension from Q to Q alpha 2 alpha 3, that has degree 12, which we know from the right-hand path here. And so on the left-hand path, we've already got a degree 3 extension, so the other extension along the path must have degree 4. So that's a lot of work, but we were able to figure out the degrees of all the extensions of all of the the degrees of all the extension fields inside this this extension. Understanding the structure of how subfields of an algebraic extension interact with each other and their various degrees is the basis of something called Galois theory. And we're actually going to be taking a look at that in a little bit. And it turns out that the relationships between these subfields is strongly connected to the sort of nets of subgroups that we looked at last semester. And Galois theory, it turns out, will combine these ideas together, the ideas of group theory and field theory together. Okay, so another much smaller example, but where we look at some of the implications of Theorem 173. So note that f, which is given by 3x to the 7th minus 6x squared plus 8x plus 10, a polynomial ring over the rationals, is irreducible by Eisenstein again, by Eisenstein's criterion. So that means that if alpha is any root of f, then the field extension Q alpha over Q has degree equal to 7. F is not quite the minimal polynomial, but if you just divide everything by 3 here, then you will get the minimal polynomial of alpha. Now, we can actually see now that the cube root of 5, for instance, is not in this field Q of alpha. No matter what alpha we choose. And this is since if it did happen, if the cube root of 5 was in this field, we would have that 7 is equal to the degree of the extension Q alpha over Q, which is equal to, by Theorem 173, the field Q alpha over Q cube root of 5 times the degree of Q cube root of 5 over Q. But the element cube root of 5 has a minimal polynomial of degree 3 over Q, namely x cubed minus 5. And so the degree of this extension here is 3. And so we have that 7 is equal to something times 3. This is a contradiction. Degrees of extensions are always integers if they're finite, and therefore we can use very simple checks of divisibility to determine that many elements do not lie in given field extensions, if we understand their degrees well enough. All right, so we've got another topic to consider with regards to algebraic extensions, and so I want to consider the extension that we looked at in a previous example, q square root of 2I. Now, we came up with this field extension in a previous lecture as the splitting field of x to the fourth plus 1 over q. And we started by taking all four roots of x to the 4 plus 1 inside the complex numbers and taking q of all four of those. And then we showed how we could reduce that, get it down to a very simple description as q of square root of 2 and I. But we can, in fact, go even further. We claim that q of the square root of 2I is actually equal to the smallest field containing just the number square root of 2 plus I. So the difference here is that here we've got the smallest field containing q and 2 algebraic elements. This is the field containing q and a single algebraic element. And the fact that we have this means that, in some cases, this will be a simpler field to work with, just because it's got a single element rather than two of them. So note that the containment q square root of 2 plus 1 containing q square root of square root of 2 plus I containing q square root of 2 comma I is obvious. So we need to show that the square root of 2 and I are both contained in this field. Note that if we take 3 times the inverse of 2 plus I, well, that certainly belongs to q of the square root of 2 plus I, because any field has to be closed under inverses and multiplication by elements of q. So this gives us 3 over the square root of 2 plus I. We can now use some standard college algebra techniques to see that if we multiply by the reciprocal here, and here we can think of doing this computation inside Q, where all of these things are perfectly well defined. And if we do that, we wind up with 3 times the square root of 2 minus I over, now the square root of 2 plus I times the square root of 2 minus I is actually 2 plus 1. And so simplifying all that out, we get the square root of 2 minus I. So this shows us that the element square root of 2 minus I also belongs to this field Q. Q adjoining square root of 2 plus I. So that means that the square root of 2, which is equal to 1/2 times the square root of 2 plus I plus the square root of 2 minus I, all these things belong to Q adjoining the square root of 2 plus I. So we have that the square root of 2 belongs to this field, and so that means that in particular that I, which is equal to the square root of 2 plus I minus the square root of 2, also belongs to our field Q of the square root of 2 plus I. So that means that the square root of 2 and I both belong to this field, and because of that, we have that the smallest field containing q and the square root of 2 and I must belong to the smallest field containing q and the square root of 2 plus I, so they are equal. So we can ask, well, when does this happen? When can we sort of collapse the generators of an extension, of an algebraic extension, down together? And the answer is many times. So let's look at Theorem 174. Theorem 174, this is the following. Let F be a field of characteristic 0, F contained in E a field extension, and A1 through AN algebraic, contained in E, algebraic over F. There exists C in E such that the smallest field containing, the small subfield of E containing F and A1 through AN is simply equal to the smallest field containing F and C. So this says that it doesn't just work for two things, it works for any finite number of algebraic elements, and you can always find a single element that gives you the same field as the smallest one containing F and a whole finite collection of them. Now, you do notice that we do have to have that the field F is of characteristic 0. It seems like when you look through the proof, we might be able to simplify that a little bit, but it's really hard to do so. I tried to find a way of writing this theorem in a slightly more general sense. I'll point out where we're using the fact that F has characteristic 0, and we'll see that it's really difficult to find a way of removing that. Now, for the proof, it suffices to prove it in the case n equals 2. So by induction, we may prove for n equals 2, because then if we have that f of a1, a2 is equal to f of c for some c, then that means that f of a1 through an is equal to f of a1, a2 of a3 up through an, which is f of c of a2, a3 up through an, which is f of c, a3 up through an, which is the smallest field containing f and n minus 1 elements. So if we can prove that we can collapse down two of them, then we can collapse down any number of them. So that's what we're going to do here. So let's suppose that A and B belong to E and are algebraic over F. And let's let F be the minimal polynomial for A. Let's let G be the minimal polynomial for B. Now let's let D in F be any element such that D is not equal to alpha minus A over times, I should say, alpha minus A times beta minus B inverse for any root alpha of F and beta other than b of g. Now, this is one place where we need that f is infinite. Now, since f has characteristic 0 in our theorem, then it's necessarily infinite. We also know that f and g, because they're polynomials, have only finitely many possible roots in any extension. And so if we take all the possible roots of f and all the possible roots of g and form this product, alpha minus a and beta minus b inverse, we get a finite number of elements of f that we need to avoid. And so if we pick any element of f other than those, then we'll be able to construct a C that works. In particular, note that in what we're about to do, almost any element of f will work. We just have to avoid finitely many elements of f. So this there exists a C in E. This C is highly non-unique. In fact, in some sense, almost, or there are lots and lots of elements of E that will work to make this process go through. All right, so we have all this, and let's let C equal a minus db. Now we have that clearly f of c is contained in f of a b, because if any field contains a and b and f, the field f, then it will necessarily contain a minus db, which we're taking to define c. So it just remains to show that a and b, the elements a and b, each belong to the field, the smallest field containing c. So to do that, let's go through the following argument. Let's let p be the polynomial in f of c join x, be the minimal polynomial of b over the field f of c. Here we're using the fact that we can do this because we have that f contained fab is finite, and so by a previous theorem we have that f is contained in f of c, which we already know is contained in f of ab. We have that the extension f of c contained in f of ab is finite, hence algebraic. So that means that b is algebraic over the field f of c, and therefore it has a minimal polynomial. Now, since g of b is equal to 0, we have that p divides g in the polynomial ring f of c join x. Now let's define a new polynomial. Let's let q be in the ring f of c adjoint x, be given by q of be given by f, or rather, sorry, q is equal to f of c plus dx. Where we just take the polynomial f, which remember was the minimal polynomial of a, and replace all of its variables x with the expression c plus dx. Now this will no longer belong to f adjoin x, but it will belong to f adjoin c, because c and d both belong to f of c. So now this q is a polynomial here, and we can note that q of b is equal to f of c plus bd, which is f of a by construction. A is equal to c plus bd, and so this is 0. So that means that b is a root of q, so p divides q as well. So that means that any root of b, any root of p rather, of p is also a root of g and q, because p divides both g and q. So let's let e, little e inside the field e, be any root of p other than b. We have then that e will be a root of q, so we have that 0 is equal to q of e, which is f of c plus de. So that means that c plus de is a root of f, and e is a root of g. Now remember that we claimed, or we selected our d in such a way that it would not be equal to alpha minus a times beta minus b for any beta minus b inverse, where alpha and beta are any roots of f and g respectively. So in particular, this means that d is not equal to c plus de, this root of f, minus a, times e, this root of g, minus b, inverse. But if we work out what this is, a is equal to c plus bd. And so if we subtract this all out, this gives us d times e minus b times e minus b inverse, which is d. So we have that d is not equal to d, a contradiction. Therefore, we can't have any root of p other than b. So b is the only root of p. And so that means that p is equal to x minus b to some power m. And here's where we're going to again use the fact that f has characteristic 0. Since f has characteristic 0, so does f of c, and so that means that f of c is a perfect field. So that means that the multiplicity of any root of an irreducible polynomial over f of c is 1. Therefore, m is equal to 1, so that means that p is equal to x minus b, which belongs to f of c adjoin x, so b belongs to f of c. Now here again, as I mentioned, this is where we need f to be characteristic 0 as well. Now, before we used the fact that f had characteristic 0 to conclude that f had infinitely many terms, or infinitely many elements. Now, we could, of course, just replace the characteristic 0 condition with the assumption that f is an infinite field in order to make that part of the process work. That's fine. But we really do need that f of c here is a perfect field. And the problem is that if f does not have characteristic 0, if it has characteristic p for some prime, then f of c will also have that same characteristic, but even if f is perfect, f of c might not be perfect. It might fail to be perfect when you move up. And so because we don't, in order to drop the characteristic zero assumption, we would have to have a lot more control about what types of elements D we're choosing, and we might have to have some control over what elements A and B we're looking at. And so if we want the theorem to be as strong as it is in terms of working for any algebraic elements A and B, we kind of have to assume that F has characteristic zero. In many situations, or in many specific situations, a similar result to this will apply even in positive characteristic, but you would need some way to know that this f of c field is perfect, which you probably have to prove in your specific situations. So that's why for this general statement of the theorem, we just assume that f has characteristic 0, therefore it's perfect, and therefore any extension field is perfect, and we're good to go. So we get that b is contained in f of c, so that means that a, which is equal to c plus bd, is also in f of c. And so that means that f of AB is contained in f of C, so f of AB equals f of C. So we've proven the result that we wanted, and as long as you're working over a field of characteristic 0, then the smallest field containing any finite number of algebraic elements can be written as a field containing just the smallest field containing just one algebraic element over your field. So taking as an example, we looked at q of square root of 2 and I, and we showed that we could write this as q of square root of 2 plus I, but let's see what other options are available going through the proof of this theorem. So we have that the minimal polynomial of square root of 2 is x squared minus 2, and the minimum polynomial of I is x squared plus 1. Now, the roots of x squared minus 2 in C, which is the field that everything here is belonging to, are plus and minus the square root of 2. Let me actually write those out more carefully, and this has roots I and negative I. So this means that we can take our C to be A plus or A minus BD, where A is the square root of 2 and B is I, so long as D is in Q, and D is not equal to alpha minus square root of 2 over beta minus I for any roots alpha, beta of x squared minus 2 and x squared plus 1, respectively. So we've got that D has to not be equal to square root of 2 minus square root of 2 over negative I minus I, and has to not be equal to negative square root of 2 minus square root of 2 over negative I minus I. We can't take a beta value of I because that would make the denominator here equal to 0. So D can't be equal to 0. We can't just take the square root of 2. And we also can't take negative 2 square root of 2 over negative 2I, which is the square root of 2 over I, which is negative square root of 2I. But this isn't in Q to begin with anyway. So our conclusion, I've run out of space a little bit here, is that the only rational number d that we disallow in this construction is 0. So in conclusion, this means that q of the square root of 2I is equal to q of the square root of 2 plus di for any d not equal to 0 in Q. So in fact, there are infinitely many different ways of writing this field as an extension over Q based on a single algebraic element. All right, the last thing that we want to do today is to prove Theorem 175. Earlier, we had a theorem that said that a composition of finite extensions is finite. Well, the same thing holds for algebraic extensions. So let's let F contained in E and E contained in K be algebraic extensions. Then the extension F contained in K is algebraic. Now, the reason why we don't already have this is that, as we've seen, there are algebraic extensions which aren't finite. However, what we can take advantage of is that if I look at any extension where I just add on a single element, a simple extension in the style of the ones that we have that we were just looking at in the previous theorem, then those extensions are algebraic if and only if they are finite. And that's what we're going to take advantage of. So let's take a proof. Let's let A in K, B in K. Now, since E is contained in K is algebraic, there exist B0, B1 up through Bn, such that A is a root of B0 plus B1x plus etc. plus Bn x to the n inside the polynomial ring E adjoin X. So, in particular, this means that the if we look at the smallest field containing B0, B1 up through Bn and A, that is a finite extension of the field containing just B0 through Bn. In fact, if we assume that this is the minimal polynomial of A, then we could say that this is exactly n. But all we really need here, all we're really going to need here, is that this is finite. Now, furthermore, we have that every FBI over F has finite degree. And so what this means is that we can take the following formula for degrees. We have that the formula f of A we've got the f of B0, B1 up through Bn A colon f of B0 up through Bn is equal to getting slightly ahead of myself, times the degree of the extension f of b0 up through bn minus bn colon b f of b0 up through bn minus 1 times the degree of f of b0 up through bn minus 1 times f of b0 through bn minus 2, etc., etc. And what we do is we look at the degrees of the extensions that we get when we go from some collection of the b's to the ones where we add on one more. And so we end with f of b0 over f. And the point is that all of these are finite. So because A is algebraic over E, in fact, and because the polynomial there's a polynomial recognizing that using just b0 through bn, a finite number of elements of E, and because adding each of these b's on is only a finite extension from your base field f, combining all those things together gives you a finite field extension. So that means that A is in a finite extension of f, and so A is algebraic over f. So that means that K is algebraic over f. And the reason why this doesn't show that K is finite over f is because the number of extensions that you need might be larger for more elements of K. Each element A might have a very large minimal polynomial over E, which means that you have a larger chain in the theorem. All right, so one of the things this means is that if we look at the set of all algebraic elements over a field F in an extension field E, we get the algebraic closure, which we usually denote F bar of F in E. What Theorem 175 shows is that if I take the algebraic closure and then close it up again, if I take the algebraic closure of the algebraic closure, I just get the algebraic closure back. Because if there was some element that was algebraic over F bar, then it would be algebraic over F. That's what Theorem 175 shows, which means that it would already be in F. It would already be in F bar to begin with. In other words, F bar is algebraically closed in E. That's how we describe a field whose algebraic closure is equal to itself, where there are no algebraic elements in the extension field that you're considering. Now, some fields have the special property that if you consider any extension field of them, they're always algebraically closed. So, the complex numbers, for instance, have this property. So C has the property that if C is contained in E is any extension, then the algebraic closure of the complex numbers in E is equal to the complex numbers. So the complex numbers are sort of universally algebraically closed. No matter what field extension you take of them, they're always going to be closed in it. It turns out that every field is contained in some universally algebraically closed field like this, but the proof of it does require some more advanced techniques that we are unfortunately not going to be able to cover here. Nevertheless, algebraically closed fields have a lot of importance to algebra in general, and in particular commutative algebra. Ring theory a lot of times is concerned with algebraically closed fields. Polynomial rings over algebraically closed fields have a lot of nice properties that are that don't hold for non-algebraically closed fields. All right, so that is the end of our discussions about algebraic extensions here, and next time we will move on and talk about some other topics.